Hello and welcome to a new calculator tutorial for the TI-84 Plus. Today we'll be discussing a few different functions, those that have to deal with probability density distributions. We'll be talking about what is the normalpdf, the normalcdf, as well as the inverse norm. Each of them have their own different uses when trying to analyze something about a normal curve. What I have drawn here is a standard normal curve and a z-score with its probability found here. I have here the z-score negative 1.24 as well as a probability shaded below it of 0.1075, indicating the probability from about negative infinity, or really low on the negative end, up to the value of negative 1.24. We're going to be able to find each of these values, either the z-score or the probability, given the other value by using the functions that I have listed. The third function, the other one, which would be normalpdf, has very specific uses, but I'll be going into that as well. So this is using a different function. I use z-test to create this, which is not going to be used in this tutorial, but I just wanted to give a good basis of what we're working with. A nice normal curve, finding some z-score, whether it's already normalized, or whether it's still in its normal form with some mean and standard deviation. But if it's already normalized with a mean of 0 and a standard deviation of 1, we can work with those as well. So to access our functions, I'm going to quit back to the menu. And since we're dealing with a normal distribution, all our values are going to be in the distribution section here above vars. So I hit second, vars, and I have three different options here. These are the three that I want: normalpdf, normalcdf, and inverse norm. These are going to be the functions that are going to give me the values that I want in a normal curve. Normalpdf will find the singular height at any given value. So if I find a z-score, I can find its given y value or its height according to the normal curve. If I have normalcdf, then I can find the cumulative probability from one value to the next, maybe from negative infinity up to a value, or from two different values on the given probability distribution. And inverse norm is going to be used to kind of reverse that. So inverse norm and normalcdf are opposites. Inverse norm is going to be able to find the z-score relative to a probability found for the left side. You'll see what I mean in a moment. So normalpdf, I'll just use one of those to kind of demonstrate what its use is. If I have an x value, maybe I have 87.6, which is the value that I used to make the previous normal curve. And I have a mean of 100 and a standard deviation of 10. If I put all these values in and paste to the front, if you do not have an 84 plus, you may not have the wizard, and you may have to put in these three values manually. I have the z-score itself, as well as the two values, the mean and the standard deviation. All these functions will always end in those last two values, so if you have to plug them in individually, keep that in mind. The last two should always be the mean and the standard deviation. If I hit enter on this, I get a value of 0.01849. Now that did not match up with what I saw on the previous graph. That was 0.10, or about 10%. This is indicating close to about 2%. But again, this is specifically for a singular probability, the height at that specific point, the height of the curve at that point. Not necessarily a full area of probability, which is normally what we wish to work with. So this has very limited uses. What we tend to work with instead is normalcdf, which again is in the same place. So if I go down to cdf, you'll notice I have a question for the mean and standard deviation yet again, but then I have a lower and an upper, because here we're trying to find an area or a range from one point up to another. In this case, I want to find the area less than 87.6. So I'm going to indicate something around negative infinity up to 87.6. Now, sometimes this negative 1 e to 99, this means negative 1 times 10 to the 99, or negative 1 times with 99 zeros. If you do not have this, this is perfectly fine. What you just need to indicate is something to represent negative infinity, or a small enough number. I typically use negative 9,999, or negative and 4 nines, or maybe 5 nines. It's irrelevant. As long as it's small enough, then it should be fine. Whether you use this or add another 9, the difference will be so negligible your calculator won't even be able to display it because we only see 10 decimal places when calculating. So here I have essentially negative infinity up to 87.6. I have my mean again is 100 and standard deviation of 10. Sorry, 1 second. Okay. Sometimes my program has a little mistake there. So when I have all the values plugged in, I want to hit paste. It pastes it to the front. Again, if you do not have an 84 plus that has the wizard, you want these 4 values. The lower, the upper, kind of like when we were dealing with random functions in the past in the previous video. So lower and upper followed by the mean and the standard deviation. Again, these are always your last 2 values. I hit enter, and there we go, 0.1075 about. This is what was displayed on the previous graph. This is saying that there's 10.75% less than 87.6. All right, great. So that's dealing with normal CDF. Now, a couple other ways you can use normal CDF. Maybe you want to find the area between 2 values, so maybe between 87.6 and 108. I can find the area between these 2 values on my range here. Paste in the same way. Again, in this case, I'm not going from negative or positive infinity. I'm just going between 87.6, 108 to find the probability in between there. And I get about 68%. So there we go. Works pretty nice. And lastly, if I want to do something else, maybe I want to find the probability greater than something. So let's do 110 up to something big enough. So like before, I'll use 4 nines just in the positive direction. This will be from 110 up to 9999. If we do this right, according to the empirical rule, since I'm 1 standard deviation away, if you notice 110 is 1 standard deviation above the mean of 100, that means I should get approximately 16%, according to the empirical rule. But since it's an estimate, it's probably going to be a little bit off. But I hit paste, we expect to get something about 16% here. And there we go, 15.87, or about 16%. The empirical rule itself is simply a guide, but this finds exact values, exact percentages based on a normal curve. So that's how you work with normal CDF. Overall, it's a pretty easy function to use, whether you have the wizard or whether you don't. Just make sure you know what your lower bound is and what your upper bound is. Maybe if you want to find 2 different tails, you may need to find the area of each of those tails, or maybe the area in between. For example, the second thing that I had normal CDF of 87.6 to 108. Well, I know that there's 68% between them. So if I think about complement-wise, there should be about 32% outside of that. So below 87.6 and above 108, if I look at both of those tails on the normal curve, I can figure that out just using complement rules, finding that about 32 or about 31.03% of the data would be in those tails. So keep that in mind. All right, so that's dealing with normal CDF. This is, again, if you're going from scores, whether they're z-scores or values given for a non-normalized curve, and we're just trying to find the percentage above, below, or between. Lastly, we have inverse norm. Now, depending on your calculator, you may have an easier time with this. However, I'm going to be doing what most 84 calculators do. If you have a higher version of 84s, then you may have an even better situation here. So what inverse norm is used for is the other way around. If you know the percentage below a given value, and you need to find the z-score that's relative to that. And specifically, inverse norm only works with the percentage less than a given value, or the percentage on the left side. So for example, if I know that on the left side of some z-score is about 24% of all my values, or about 0.24, I could find what z-score would be relative to that. According to the empirical rule, I expect this to be somewhere between 0 and -1 on the z-scores. But let's see. if I use my previous values, maybe I use 100. Let's do 0, so I have a normalized curve. Yeah. So let's say between 0 and 1 for my mean and standard deviation. And I want to find the z-score that says 24% is less than that. I paste that in, and there we go. This is exactly what I expected, somewhere between 0 and -1. This is saying that the z-score of -0.7063, there's 24% below that, and likewise, there's also 76% above that, if I think about complements. So this is how inverse norm is used. If you have a higher version of 84s, you may have an easier time with inverse norm because there are 3 different other values that you can plug in. You'll see on the bottom when dealing with inverse norm, I'll go back to my function. When dealing with inverse norm, you'll have these same 3 values, but you may also see a row here saying left, center, or right. This is indicating what tail you want to calculate and what does this area refer to. Does it refer to an area on the left side of a z-score? Does it refer to the area on the right side of a z-score? Or does it refer to an area between 2 given z-scores? And that would be something around the center. So that means you'll have a little bit of an easier time working with this. If you don't have that, you might need to do a little bit of math. For example, say I have the middle 30% refers to 2 different z-scores. So surrounding the mean, I want to find what z-scores refer to the middle 30%, right in the center. Because I have a symmetric, I'll even have a little graph up here. If I think about this, the middle 30% would be something around here. And I want to find what z-scores refer to the middle 30%. Now, if you have the other 84, the one that does have the middle or the right, center, and left values, then you can have an easier time with this. You just need to put in the area of 0.30 and select that you're working with a center, and it'll give you your 2 z-scores. However, I will be assuming that you don't have that, and we'll only be using inverse norm as it is originally intended, which means the percentage less than something. So, if I have the middle 30%, then mathematically, the tails together, each of the tails would add up to 70% by complements. The middle 30 and the outside 70. With that in mind, that means whatever each of these z-scores are, I know each of them together, each of the tails refer to 35%. Because if I put the 2 tails together and that's 70%, divide them by 2 because I have a symmetric distribution, then each of the tails refer to 35% on their own. Meaning that this lower z-score refers to 35% is less than that value. So I can use inverse norm in that way. Let's go to inverse norm. Area of 0.35, so whatever z-score means that 0.35 or 35% is less than that. Again, it should be somewhere between 0 and -1. And I have mu and sigma. Paste that in, and I should get -0.3853. Now that refers to one of the z-scores. If I'm dealing with the middle 30%, then there's 2 of them. Well, because it's also symmetric, that means the one that's on the other side, the one that's on the positive end or above the mean, should have the exact same z-score. The positive version should have a value of 0.3853 with no negative there. Meaning I don't need to do extra work, I just need to think about how symmetry works. However, to prove that, let's go back to inverse norm. Well, the lower z-score had 35% less. The higher z-score would have 65% less. The reason is either 2 ways to think about it. One, there's 35% greater than the higher z-score, which means there's 65% less than it. Or, I know that the higher z-score has both the middle 30 below it and also the 35 tail, which is what we just calculated here. Meaning together, 30 and 35 is 65. So this should be 0.65 if I want to find the upper tail. And if everything works out right, we better get 0.3853204.726. And there we go. We get both these answers. Now again, if you have the other 84 that has that row for right or left, center, and right, then you might not have to do this. You can just use center. It'll give you both the z-scores, which is going to be both of these. However, if you don't have it, you can still work with it perfectly fine, just like we did here. Just might need to do a little bit of probability logic or some mathematics here to calculate some probabilities. The last thing to keep in mind with inverse norm is that it's often used with what is called a z sub alpha value. The z sub alpha refers to what z-score such that a given percent or a given proportion is on the right side of that z-score, and specifically it's on the right side. I think I was taught in a previous class it was on the left side, but it's typically referred to on the right. So if I have a z sub alpha value that says z sub 0.20, that means I want to find the z-score that has 0.20 on the right side of it. So if I think about the graph, something that has 20% on the right side of that unknown z-score. Now, because I'm working with inverse norm always works with the percentage on the left, so that means I need to do a quick complement calculation. If there's 0.20 on the right, then that means there's 0.80 on the left. 1 minus 0.20 gives you 0.80 or 0.8. So, to find that z-score, I do inverse norm. Area of 0.80 is on the left. This is how inverse norm usually works. Mean of 0, standard deviation of 1. This will find me the z-score that has 80% on the left and 20% on the right. And we get a positive value, which is again what we expected. 0.8416. So the z-score of 0.8416 has 80% below it and 20% above it. And that's one pretty common application of using inverse norm, is working with z sub alpha values, which is just one way of notating how to do these z-scores. Instead of writing it out of what z-score has some percentage above or below it, we tend to just talk about find z sub 0.15 or z sub 0.12. That would indicate what's the z-score that has 0.12 on the right side. It's always saying the right. And if we're doing inverse norm as it is, we have to do it on the left. Now, last time, if you have the 84 that has the left, center, or right designation, then you don't have to worry about this. Just know what tail you're working with or what side of a probability you're working with and indicate that on your selection. With that said, that's everything that I want to talk about today. Dealing with normal distributions, we had those 3 different functions. If you have any questions, please feel free to put the questions in the comments below, or if you're one of my students, feel free to just come up and ask me. I'll see what I can do. With that said, I will see you in another video.